Today's our topic is PN junction diode. So in this PN junction diode, here we have P type semiconductor, and whenever it is joined with N type of semiconductor, that type of arrangement we call it as PN junction diode or a semiconductor diode or a crystal diode, but mainly we known it as PN junction diode, right? Now here we have P type semiconductor and N type semiconductor. So in between these two semiconductor we are having one wall, right? So P type, we know that P type means positive, and positive semiconductor having more holes. N type means negative, negative type of semiconductor having more number of electrons, right? So mobile hole, majority carrier in N, it is electrons, and majority carrier in P type of semiconductor is holes, right? So here these are majority carrier and minority carriers, right? So that we know that. Now N region has mobile electrons negative and immobile means less positively charged ion. So here we are having hole arrangement as neutral, because P have is, for example, P are having number of holes is same that N are having number of electrons, right? So PN junction diode, immediately after it is formed, we are having one region like this. This is one region between P and N junction. This is called junction, right? So junction, and near to that junction we are having one region which is called depletion layer, right? So here see, we can see that from negative charge that electrons are moving towards this region, and we can also say that holes are moving in this region, right? So like this we are forming now electric field, and always electric field is from positive to negative charge. So we are having electric field inside this region which is in left hand side direction, right? So here PN junction diode is formed. So here concentration of P means holes and electrons are changing. So free electrons from N region diffuse into P region due to some reason, right? Why electrons are moving from N to P? Because electrons are always at high potential. So N is always having higher potential than P type semiconductor, and because of that higher potential, electrons always moves from higher potential to lower potential, right? So here each recombination eliminates an electron and a hole. Electrons are moving towards hole, they recombine, and then after that some particles left neutral, right? So here uncompensated negative immobile ions in the P region do not allow any more free electrons to diffuse from N region. So that is our PN junction diode. So here, yeah, that region is called depletion region, as I said earlier. So here region having only immobile charges, therefore this region is called space charge region. So always N region is having higher potential than the P region, right? So always electric field direction is from positive to negative. Now whenever electron there are many electrons in P type of semiconductor also, right? So if that electron wants to come towards N type of semiconductor, that electron have to have to achieve that potential barrier, because if that potential barrier just stops that electron to come towards the N type of semiconductor, right? So different semiconductors having different width of barrier is, for example, for silicon 0.7 volt and for germanium 0.3 volt. See, potential barrier is in the form of voltages. So whenever electron gets this amount is, for example, in silicon, then electron can move easily from one semiconductor to the other, and germanium having lesser energy, 0.3 volt. So electron can get this amount of voltage, then electron can move easily towards one, from one semiconductor to another semiconductor. So here, whenever, if majority carriers having high kinetic energy, it can manage to overcome the barrier, right? Because kinetic energy means whenever velocity of electrons having it have higher value of that energy, that motion, then kinetic energy will be more, and because of that, that electron can move easily, and it can come out to other semiconductor. Now yes, we are having two biases. Our first bias of PN junction diode, see, we are having two bias according to PN junction diode, that depends upon us, right? So two types are that, first is forward bias and second one is reverse bias. So first, forward bias. Now what is the meaning of forward bias or in PN junction diode? The meaning of forward bias, that positive P type of semiconductor connects with positive type of battery, positive terminal of battery, and negative semiconductor should connect with negative terminal of the battery. So positive to positive, negative to negative, then we can call it as forward bias of PN junction diode, right? So here, see, here we are having some battery, right? And as we can see that this positive terminal connects here with the positive type of semiconductor, right? And here this negative terminal connect with negative, right, negative type of semiconductor. So here we are having forward bias of PN junction diode. Okay, now exactly what happens here, here we have one depletion region. Between that junction, near to that junction, we are having depletion region, right? So electric field is always from positive to negative inside that depletion region, right? But outside that depletion region, we are having this P type of semiconductor, this is N, that's why outside we are having electric field towards the right hand side direction, right? So inside left hand side, and here outside which is right hand side. That's why, because of this differences, see, this is inside electric field and this is outside electric field. So here difference, because of this difference, we are having as a result electric field which is in right hand side direction, because this value of electric field is more than this value, right? So as a result, we are having electric field in the right hand side direction, and because of that electric field, because of that opposite of this electric field, this depletion region in forward bias, its width is very small. So always remember, depletion region for forward bias, its width is always small, right? And whenever width of depletion region is small, electron can easily move from N type of semiconductor to P type of semiconductor. And whenever electron can easily move from one type of semiconductor to another type of semiconductor, current can easily pass. So in forward bias, we are having more current, larger value of current, right? So that is the effect of forward bias. So for each electron hole recombination, an electron from the negative terminal of the battery enters the N region and then drifts towards the junction, right? So see, always because of this motion of electrons, we are having more value of electric current, right? So here potential barrier, the width of potential barrier is decreased, and because of that electron can move easily from one region to another region, right? So now we are come to the reverse bias topic. See here, reverse bias, it is completely opposite to that forward bias. Here we are connecting battery's negative terminal to positive terminal of the semiconductor, and positive terminal of the battery should connect with the negative of the semiconductor, right? So here we are having connection like this. So see, earlier we are having that similar, see, as we can say positive, this is positive, this is negative, right? But because of that we are having now outside electric field left hand side because of this battery. Inside means depletion region, we are having electric field which is also in left hand side. Because of same direction of this electric field we are having larger width of depletion region. Now here, as we can see from the figure, we are having larger width of this depletion region, right? So now electron can't be easily come out from the negative type of semiconductor to positive. So now electron having more potential barrier. Now electron want more energy to come from negative to p type of semiconductor. So here, yeah, now depletion region is more than the previous one. Earlier we discuss about forward bias and we are having depletion region which is smaller than the reverse bias depletion region, right? So now in this reverse bias electron can easily, in this, sorry, electron can't moving easily from negative type of semiconductor to positive type of semiconductor. That's why here we are having very less current value. So whenever we reach that lesser value of the most lowest value of current, that is called reverse saturation current. And now for reverse bias we are having this order of currents 10 raised to minus 9 ampere to 10 raised to minus 6 ampere. So for this order, 10 raised to minus 9 means nano ampere, and 10 raised to minus 6 ampere means micro ampere, right? So yeah, now characteristic of forward bias and reverse bias. Characteristic means we are now drawing the graph according to forward bias, right? So this is the circuit diagram of forward bias. So see, as we can see that this is positive should connect with the positive terminal and negative should connect with the negative terminal, right, which is shown in this figure. So yeah, to know which value of current we are having in this forward bias, that's why we connect milliampere. So milliampere range means 10 raised to minus 3, right? And to find that voltage, because here we are finding characteristic means graph, and now we are drawing the graph of voltage versus current, right? So see here voltage, and in y-axis we are having current, right? So see, if means forward bias, vf means forward bias. So I and v forward bias current and v forward bias voltage. So for forward bias we are having this graph characteristic which is not straight line, means in this particular biasing we are not having I is directly proportional to v. It is not directly proportional, it is non-linear. So here this forward bias, this diode characteristic is not obeying Ohm's law. Ohm's law told that current should be directly proportional to voltage. So for a very small region we are having this linear region which is not so much large, otherwise we are having curve region, right? So now we have to talk about reverse bias. Now see, reverse bias, we can see that this positive terminal connect with negative and negative connect with positive, that is our reverse bias. So similarly here again we have to draw graphs. So see, voltage, current, right? So in this graph, see, we can see VR, reverse bias voltage, reverse bias current, right? So graph should be like this, which is again non-linear. Now after certain point we get voltage, it is constant, right? So right, resistance of a diode, if you want to find resistance, then we a smaller value of resistance, right? We have to take smaller value of voltage as well as current, then we can find resistance easily. So resistance of a diode is a dynamic or AC resistance. So here RAC is equal to delta V upon delta I, means smaller value of voltage, smaller change in voltage upon smaller change in current.